The Part Builder tool from CAD Enhance can build schematic symbols for FPGAs using two different methods, referred to as the FPGA Physical and FPGA Logical flows. While CAD Enhance supports these flows for Xilinx, Altera, and Lattice devices, in this video we will compare and contrast the two methods used to create the symbols for a Xilinx UltraScale Plus FPGA in a 1517-pin BGA package. We will be highlighting the significant reductions in development time and connection error risk provided by Part Builder's logical flow. The extra design flexibility offered by the logical flow should become readily apparent. A quick peek at the top-level Verilog for this design reveals that we have a PCIe Gen 3x16 interface, a high-speed memory interface, a 4-lane QSFP28 interface for 100 gig Ethernet, two DDR4x72 interfaces with 18 strobes, and a lot of pins for board management. Part Builder's FPGA physical flow is extremely efficient and is used to build symbols based on the physical bank layouts and the generic I/O pin names that the FPGA vendors assign to their parts. Part Builder uses the package file available from the vendor as the source to accurately extract the pin data. Using the physical flow, very functional groups of symbols for FPGA devices with 50 to 2,000 plus pins can be easily created in under an hour. The FPGA logical flow builds symbols for the FPGAs using the logical pin names from the actual FPGA application, which get assigned to the physical pins by the FPGA compiler tools. A unique set of symbols is built to represent the FPGA device based on the application of that device in the design. Part Builder combines the data from the FPGA compiler pin report and the package file from the vendor to extract the pin data for the logical flow. Depending on the size of the design, symbols for the FPGA and the logical flow can be created in 30 minutes to a couple of hours. Extra time spent up front carefully planning meaningful pin names for the application and crafting the SDL to create functional symbols for the logical flow can save the engineer time measured in hours, days, and even weeks. This is because the logical flow dramatically improves the process of connecting, verifying, and updating the FPGA pin connections in the design. The logical flow can also add pin swapping and gate swapping controls to the FPGA pins, which are not possible in the physical flow. Let's take another look at the symbols we created for the Xilinx part using the physical flow. We can see multiple symbols containing the pins for the 10 groups of high-speed transceiver banks, organized in pairs as they appear in the part. We needed to look in the pin report file to group them for their intended functions for PCIe, high-speed memory, and the QSFP interface. Another group of symbols contain the pins for the 10 general-purpose I/O banks, again organized in pairs. Some designers like to have the I/O power pins co-located with the I/O pins, and some like them on a separate symbol. Here they are built together. Again, we group these using the pin report to find the proper banks for the Channel 0 DDR interface, the Channel 1 DDR4 interface, and the management interface. The other symbols house the FPGA config pins, the MGT power and support pins, the core power pins, and the ground pins. Part Builder's symbol description language with its support for looping makes it incredibly easy to define and change the grouping of the transceiver pins and I/O banks to create a set of symbols that satisfies the requirements of both the engineers and the librarian. Now let's look at the symbols created for the same FPGA device using the logical flow. We have symbols for the PCIe interface, the QSFP interface, the high-speed memory interface, the two DDR4 channels, Channel 0 and Channel 1. We have another symbol for the management interface and one for the x86 analog input pins. It is pretty obvious what pin should connect to what signal for these blocks. Then we needed to create two symbols for the spare I/O pins and two for the spare transceiver pins. These are drawn much like they are in the physical flow. We also created two symbols to house the left and right side I/O bank power pins. Finally, we can see the FPGA config pins, the MGT power and support pins, the core power, and the ground pins. These last symbols don't really change between the physical and logical flows and can share the same SDL to create them. It is interesting that the symbols drawn with the logical flow, like the one we created for the high-speed memory interface, can contain a mix of high-speed transceiver pins for the diff pairs and general-purpose I/O pins for the I2C and status and control pins. This really helps with schematic readability. We are viewing these symbols as they appear within the Cadence Allegro HDL tool, but Part Builder can also build the symbols for the OrCAD, Eagle, and DX Designer schematic capture tools, and support for PADS and Altium will follow shortly. Engineers and librarians are probably most familiar with symbols built using the physical flow. One reason for this is that it used to take so much time to build the symbols for an FPGA that it made sense to build one set of symbols representing a specific device and then reuse the same set of symbols in any design that used that FPGA device. It seems that no one was thinking of the burden that this placed on the design engineer, who was left with the mind-numbing task of interactively connecting the large set of generic I/O pins in the schematic. While some clever engineers develop scripts and tricks to help them perform this task, it remains a mostly manual process of wading through the detailed FPGA pinout report in 3 passes. The first pass through the report looks at the bank pin assignments at a high level to figure out the best way to group the I/O bank symbols in some functional order in the schematic pages. Here, for instance, we know that the DDR4 channel 0 signals are connected to banks 44, 45, and 46, so we place them on one page. Next, we search, and we see that the PCIe connections are using transceiver banks 224, 225, 226, and 227, so we find those symbols and place them on the The second and most time-consuming pass is to look at each signal assigned to each I/O pin and create a wire with the same or similar name for each pin in the schematic. We will add just a few here on the channel 0 DDR4 block just to show the painful process, and we will speed it up too. With the 1517 pins in this device, it is clear that it is not a quick or trivial task, and it can be prone to user entry error even with the most careful of designers. The third and equally important pass is to go back and verify that every pin was connected correctly. Now, if a pinout change is needed to optimize internal routing and or board routing, or a device change is needed late in the game because the FPGA might not have enough resources to support its design intent, the engineer is left to reshuffle all the pin connections and or reconnect the whole device again. Now let's contrast the process when we use the logical flow. Figuring out how to lay out the symbol sections was almost done for us when we designed the symbols using the SDL. There's a functional block for the QSFP, one for the PCIe interface, one for the high-speed memory interface, and one for each of the DDR channels. Easy. When making the connections to the symbols, the design engineer has no need to look up pin names in the pin report file. Part Builder already did that for them when it extracted the pin names from the report. They can wire to the FPGA using existing pin names as a guide, which provides a huge time saving, provides a visible means to check the connection names, and greatly reduces the risk of manual connection errors. If the pinout requires a change, the engineer just needs to rerun Part Builder with the newly updated pin report files, and then update the symbols in the design. The symbols will stay the same, but the pin numbers will be automatically updated for each of the logically named pins. If the FPGA device is changed to a larger or smaller package, the logically partitioned symbols stay the same, and the engineer just has to make fixes to the power and support pins which may have changed. With the logical flow, the engineer's job is to connect the part once and be sure that the symbols are updated if any pin changes are needed. After watching this video, I hope the advantages of the FPGA logical flow are clear to the user. The logical flow provides a more readable schematic, a huge time reduction in making connection to the pins, risk reduction in making the proper connections to the pins, a visible means to check that the pin connections are correct without cross-referencing the pin report, and adaptability to pin/device changes with just a simple symbol update. Thank you for watching. Part Builder is available for a free download at the www.cadenhance.com/free-tool-downloads link, and a one-time 30-day license for the full tool features will be provided to the user on request. The control files used to create the physical and logical symbols used in this demo can be downloaded directly by the tool so the user can experience the design flow for themselves. Thanks and have a great day.